Okay, we're going to get started. So we're going to continue on for just a little bit here to talk about buffers. So again, like we're going to start a buffer lab, I think next week. That way, you'll have hopefully a better understanding of what's going on Tuesday. So we just talked about the common ion effect, and we'll take a look at this problem here. We want to calculate the pH of a solution that is 0.2 molar acetic acid. That's A. And B, we will get to in just a second. So why don't you just focus in on A first and give it a go. The Ka value for acetic acid there is on the bottom, 1.8 times 10 to the minus 5. And we'll go over it in just a second here. So just work on A. Okay, let's take a look, see how you're doing. So on this very first one, we're looking for the pH of a zero point 0.2 molar acetic acid solution. So what we have going on here in part A is just a weak acid, and it is a 0.2 molar acetic acid. We do have the Ka value given to us 1.8 times 10 to the minus 5. So since this is a, hang on one sec here. Sure. Going on here is just this weak acid. So it's just really a Ka problem like we did in the previous chapter. So to solve for the pH here, we're just going to dissociate our weak acid into H plus and acetate. And we're just going to do a regular ice table. We have the concentration of our weak acid, which is 0.2. This is 0 and 0. Change here will be minus x plus x plus x. And again, at equilibrium here, we'll end up with 0.2 minus x, x, and x. So this is really just a basic Ka type table like we did previously. We'll go into our Ka expression here, which is our products over our reactants. And that's going to equal our 1.8 times 10 to the minus 5. Popping in our values there, x squared divided by 0.2 minus x. Again, we're going to assume x is equal to 0, give it a shot. That will then give us x squared over 0.2 equals 1.8 times 10 to the minus 5. Again, we're going to multiply it followed by a square root afterwards. And that's going to yield us an x value here of 0.2 times 1.8 to the minus 5. It's going to give us an, I should probably square root it as well. Would be a good idea. There you go. And a little square root action, 0.001. I'll call it 90 in this case. And just make sure I punch that in there, corrector. Little square root. We do want to check it, so we'll divide it by 0.2 times it by 100%. And I think we should hopefully be okay in this case. And we are. We're about 0.9%, which means the check is good. So in this case, we can see that the H plus concentration is equal to X. So the concentration of H plus will equal our X value, 0.00190. That means we could then go right into our pH at this point and get our kind of opening pH here. And if we do that, a little minus log action, 0.0019, going to give us an opening pH here for our acetic acid of 2.72. Any questions on that one there? So this is really just a basic weak acid problem like we did in the previous chapter. Obviously, we can do our assumption here. So in the second part of this problem, we're going to keep our acetic acid here at 0.2 molar. And we now want to know what effect it would have on the pH if in addition here in B to our 0.2 molar acetic acid, we also threw in there 0.3 molar sodium acetate. So now we're going to kind of put both of these things together in the same beaker. And so let's take a look at how we could approach this problem here. So here in part B, we're going to take our 0.2 molar acetic acid, and we're going to dump in there with it 0.3 molar sodium acetate. We still have the same Ka value there, which is 1.8 times 10 to the minus 5, which again is the Ka value for our weak acid in this case. So out of these two things, we have a weak acid like we did in part A, and we also have here a salt. So out of these two things, when they go for a swim in the beaker, only one of them is going to actually set up an equilibrium, and it is going to be our weak acid. So that's really what you want to focus your equation on and your reaction on here, is the one that's going to set up the equilibrium, which is our acetic acid, going to again break apart into H plus and acetate. And once again, that is the Ka value, obviously, that goes with that. Now, our sodium acetate here is not going to set up an equilibrium. It is a strong electrolyte. It is going to simply just break apart into the ions. And it will break apart into a sodium ion and a acetate ion. Now, hopefully at this point, you can recognize that perhaps we have our common ion situation again happening here, as we have in that beaker some acetate being supplied by the sodium acetate, and we also have some acetate that's just simply being supplied by the acetic acid breaking apart. So we really have kind of two sources there in the beaker of acetate, one from the equilibrium being set up, and one from the addition of our sodium acetate into the beaker. So this will affect really our ice table in a certain situation. So initially here, we do have 0.2 molar of our acetic acid. We have 0 of our H plus. Now, where it affects it is because we also added the sodium acetate in there with it. This here will not be 0 because we're going to have a good source of sodium of acetate from the sodium acetate. So the sodium acetate here is going to provide that initial jolt of acetate, and that's going to be supplied, and it's going to be 0.3 molar because it is a 1-to-1 relationship between sodium acetate and acetate. So the important part here is you actually do need an opening concentration there on the right-hand side. And that's really important because if you zeroed that out, what calculation would you be doing? You would be doing part A again. Yeah, you basically just be doing the weak acid. So with the presence of the common ion, that sodium acetate is going to supply that 0.3, and that is where that's coming from. The rest of the table does look fairly similar. We're going to go minus x, plus x, plus x, and at equilibrium, 0.2 minus x, x, 0.3 plus x. Any questions first off on that table there? Like normal, we're going to go into our Ka expression for acetic acid because, again, it is the only thing here that's going to set up an equilibrium. And putting in our numbers, we will get our equilibrium line x times 0.3 plus x divided by 0.2 minus x equals 1.8 times 10 to the minus 5. I've had a pretty good run of assumptions here, so why not continue? We're going to assume x is equal to 0. That's going to get rid of pretty much all the x's but this x here, and we'll have 0.3 and 0.2. And that equals 1 times 10 to the minus 5. We're going to multiply that to the other side, take this guy afterwards, and divide it to the other side. And if we do all that, we'll take 1.8 to the minus 5 divided by, no, multiplied by 0.2, then divided by 0.3. And that's going to get us here an x value of something like 1.2 times 10 to the minus 5. Once again, we do need to check it. We'll divide it by 0.3 and times it by 100%. just to make sure we're okay. And we should be, we're nowhere even near 0.1%. So this check is good in this case. That means that in terms of our H plus concentration in this solution, that is what H will equal. So this equals the H plus concentration. Put a little molarity there. Now our pH would then be minus the log of 1.2 times 10 to the minus 5. And that's going to get us here a 4.92. First off, any questions on that calculation? Yeah. Correct. Yeah. Yeah. So again, you would have to do something like Q, like the reaction quotient, yeah, and compare it to the K value. I would say in most cases, you're not going to probably have that situation. So in most cases, it's fairly safe to assume it's going to go to the right. But just like normal, all these things, even though it's sort of different K is KA or whatever it is, they're all still equilibrium expressions, which means if you happen to have everybody there, you could calculate Q just to verify which way it needs to shift by comparing the Q to the K. And that would be the only way you could do it if you did have obviously everything here, and we don't in this case. So I would say again, most cases it's probably just safe to assume it's going to the right. So, other questions? Now, what did we see here? Well, when we look at the acetic acid without the common ion, we had a H plus concentration of 0.0019 and a pH of 2.72. With the presence of the common ion, we see that the H plus concentration went down to 1.2 times 10 to the minus 5. It got lower. It got lower because of this common ion being here, going to cause the equilibrium to shift to the left and keep the weak acid together. That's going to result in less H plus, as we can see here in the calculation, compared to part A. And also results, as we also talked about, a rise in the pH in comparison to the pH in part A. Part A is 2.72 because less H plus came off because of this suppression of the weak acid. That means we actually have less H plus free in the solution. The result of that is we actually are to put the higher pH than when the common ion is not present. Any questions on that there? So common ions, as we will talk about here in a second, is essentially what is happening in buffer situations. And when you have a common ion situation, or really you have sort of a buffer situation, there is a couple of things that commonly happen. And what commonly happens because of this common ion being present, when you look at the initial concentrations of these guys here, so when you look at this initial concentration and this initial concentration, and you look at the change here that you got, when you put that change back in at the equilibrium line, pretty much the initial concentration of both of those guys and the equilibrium concentration of both of those guys are essentially the same. It did not change very much. In this case, it only changed by 1.2 times 10 to the minus 5, or 0.00001 molarity, basically, right? So there wasn't a giant change that occurred from beginning to end because, again, the equilibrium is pushing back to the left there and keeping everybody together. So the good news on that, when you have a common ion situation, which again is really a buffer situation, you could actually avoid using the ice table, and you could use what is known as the Henderson Hasselbalch, David Hasselhoff equation, whichever one you want to call it. The Henderson Hasselbalch equation here. And the Henderson Hasselbalch equation is what we see there in the box. It is the pH is equal to the pKa plus the log of the base concentration divided by the acid concentration. To calculate the pKa value, you take minus the log of the Ka value. So in these situations, you actually can use the Henderson Hasselbalch equation, and you do not need to do an ice table, but you could still do an ice table if you don't want to use the Henderson Hasselbalch equation. Now, I would always use personally this version of the Henderson Hasselbalch equation, and the reason for it is in most cases you're interested in the pH. So why not just use the equation that's going to give you the pH? What I'm talking about is there is actually, much like there's pH and POH, there is a POH version of this equation. And the POH version of this equation is the POH is equal to the pKb plus the log of the acid over the base. It is reversed. And the pKb is minus the log of the Kb value is how you solve for that. So sometimes people in a basic situation will kind of use that version of it. But in this case, you still need to subtract 14 to get to the pH anyways. So why not just go into the Henderson-Hasselbalch equation there in the box? It will give you probably what you're looking for. You can use the Henderson-Hasselbalch equation for any type of situation, acidic, basic, neutral, doesn't matter. You could put all that stuff in there. But pKb can be useful because there is actually a relationship between the pKa value. If you take a pKa value and you add it to a pKb value, it equals our friendly number of 14. Much like if you take the POH plus the pH, it equals 14. If you take the pKa plus the pKb, it equals 14. Why might that be helpful? Well, maybe you got like a Kb value and you need a pKa value to go into the Henderson-Hasselbalch. You could calculate the pKb, subtract 14, and you have the pKa value relatively quickly. You could go into the Henderson-Hasselbalch equation. So I show this, and I would probably not recommend using those two equations because, like I said before, most of the time that is what you're looking for, which is pH. Again, why not just put it into the equation? It's going to give you the answer that you need. So, but again, sometimes people kind of use the other one for it. So, how do we use something like this? Let's just take a look at the example we just did. So we just did that example using an ice table, and we had 0.2 molar acetic acid and 0.3 molar sodium acetate. And we had a Ka value of 1.8 times 10 to the minus 5. Now, the first thing that you really want to know is, are these two things related to each other? And the relationship we're looking for really to help you know, should you use that equation or not, is really the Bronsted-Lowry definition, which is in order for something to be related to each other, the only difference is a 1H plus, right? So remember that this is a salt, which is really sodium and acetate. So really the two things that are related to each other is the acetic acid and the sodium acetate, and that difference is just 1H plus. So when you see that and you have a weak acid or even a weak base, you are good to go right into the Henderson-Hasselbalch equation, which is pretty much the equation you use for buffers. And we're going to take the base over the acid, the concentration of the base over the acid. So the first thing we want to calculate is the pKa, which is minus the log of the Ka value minus the log of 1.8 times 10 to the minus 5. That's going to give us a 4.74 in terms of our pKa. We can now put it into this equation. pH is equal to 4.74 plus the log between acetic acid and sodium acetate. Which one's my base? Trick question. Between acetic acid and sodium acetate, which one should be my base? That would be a good answer, yes, because I'm assuming the one that ends in acid is probably not my base, right? So sodium acetate here is my base, right? Acetic acid is obviously my acid. Just in case in trickier situations where maybe you don't know the name of the things, typically an acid has to do what? It has to be able to give away a hydrogen. So typically in the combination there, the one with more hydrogens is usually the acid. The one with least hydrogens or one less hydrogen is usually the base. And usually the base will have some type of spectator ion, like we see there, like a sodium, a potassium, a lithium, something like that, like we see with sodium acetate. So that's important because we do want to put the right concentration. So this is my base and this is my acid. And we're going to go with the base up on top and the acid on the bottom. And now if we put that in there, we're going to go 0.3 divided by 0.2, take a little log action, and add it to 4.74. That's going to give us a 4.92 pH, which, if I am not mistaken, was the same number we got over here when we did it with our ice table. Yeah. So in this situation, because it is a common ion situation and really a buffer situation, you actually do have options. If you want to do the ice table, you can do the ice table. It may be a little bit less error prone if you do use the Henderson Hasselbalch equation, but as you can see, they both will give you the same answers. So if for some reason you can't remember, should I use it or not, you could always just roll with the ice table and you get it. The important part though, if you do choose the ice table, which is again a super common error that people make, you have to have that second initial concentration on the other side. Otherwise, you're not doing a common ion or a buffer problem. You're just doing like a weak acid problem or a weak base problem. So you got to have those two initial guys in the table, one on each side, in order for it to be correct. And again, that, like I said before, is a very common error. People always kind of zero out the right-hand side of it when they're doing it. Any questions on that? Now, with that being said, it should also be said that you should be very cautious because sometimes people go, cool, I learned finally an equation. I'm just going to use it in every situation. And if you don't want X's on your paper, you should not use it in every situation. This is only, like I said before, a situation where it is a common ion or really a buffer situation, which is the same thing. It's the only time you should whip that out. If you're using that in any other situation than a buffer, you probably should just mark the X yourself because it's probably going to be wrong. And again, people use it all the time in the wrong place because as they go through their ice table and they end up with two numbers, they go, cool, two numbers. I need two numbers for that equation. I'm just going to put them in there. And again, try not to use it in the wrong situation. All right, so why don't you give this one a go? What is the pH of a solution that contains 0.3 molar formic acid, I think they call that, and 0.52 molar potassium formate? Okay, let's take a look. So once again, you want to kind of maybe figure out what's going on and what you got going. So we see this guy here, which looks similar to this one. I do kind of see a potassium in that one. This one's got a couple more H's or an extra H in there. So hopefully you can recognize this is probably your acid. This is your base. And that means that this Ka value does go with that acid there. That also tells you this is a weak acid and is conjugate base, which means that's pretty much what you need for a buffer and what you need to use the Henderson Hasselbalch equation. So once again, in this situation, if you chose to want to do a table, it would be the weak acid. Most likely, you would set up the equilibrium of it dissociating into its ions. And remember here, this kind of potassium formate here is a salt that will break apart into HCOO minus and K plus. So again, out of those two things, it's only going to be our weak acid that's going to set up the equilibrium in the solution. And if you did the ice table, you would take the initial concentration here of your acid. This would be 0. And once again, it is the salt here that is supplying the other amount of our initial concentration of 0.52. So once again, if you chose the ice table, that is super important. Otherwise, again, you're not doing the right calculation if you zero it out on that right-hand side. Change, again, going to be minus x plus x plus x. This is going to go 0.3 minus x, x, and 0.52 plus x. Obviously, at this point, you could go into your Ka, you could get your x, which will equal your H plus concentration, and then obviously into your pH. Now, if you want to take that route, that's perfectly good, but you can, again, skip that, and in this case, you can use the Henderson-Hasselbalch equation, and you'll get the pH is equal to the pKa plus the log of the base over the acid. Here we will get the pKa value by taking minus the log of the Ka, which is 1.7 times 10 to the minus 4. That's going to give us a 3.77 pKa value. So the pH here will be 3.77 plus the log of our base. Once again, as I mentioned earlier, one less hydrogen and probably a spectator ion hanging out there with our base. So we want to go with 0.52 up on top and our acid on the bottom there, 0.3. We go 0.52 divided by 0.3, little log it, and a 3.77, maybe one less 7. It's going to give us a pH, in this case, 4.01. That should be the exact same pH if you chose to do it with the ice table. Yeah. Any questions on that there? All right, so this is common ion. This is Henderson Hasselbalch, and again, really where we see common ion pretty much is what we call buffers, and buffers are definitely a common ion situation. So let's talk a little bit about buffers and what they are. So a buffer solution is a combination basically of one or two things, and it has to be pretty much a combination of either a weak acid and its conjugate base. And usually it's referred to as the salt of its conjugate base. And all that really means is there's some type of spectator ion there. There's a sodium, a potassium, something like that. Or you could have a buffer of a weak base and its conjugate acid, or the salt of its conjugate acid is more how it's usually referred to. Both of those things have to be in the solution to begin with in order for it to be a buffer. So you got to have both of those things hanging out in the solution. So what is a buffer? A buffer is a solution that resists changes in pH even when you add more acid or base to it. A misconception about a buffer is that it is a neutral solution. It does not necessarily have to be a neutral solution. You can absolutely have a buffer that is neutral. You could also have a buffer that's acidic. You could also have a buffer that's basic. You could have a buffer at any place you like along that pH scale to make it. So you can have acidic buffers and basic buffers. The idea behind a buffer is if you have a buffer at, say, a pH of 4 and you add acid to it, it will hang out around a pH of 4. It will go down a little bit, but not a very big jump in the pH. If you had a buffer at a pH of 4 and you added base to it, it will basically stay at 4, but the pH may go up a little bit. You will not see really big jumps in pH, and that is because of what the buffer is made out of. A buffer cannot be made out of a strong acid or a strong base. So you cannot have a buffer that you're like, this is a buffer and it's made out of a strong acid or strong base. The reason for that is, as I mentioned before, you have to have both of those things in the solution to begin with. You have to have like an acid part of the buffer and a base part of the buffer. So for example, if I'd made a buffer out of hydrofluoric acid and sodium fluoride, when I put hydrofluoric acid into a beaker, it is a weak acid, which means it will set up the equilibrium in that beaker and produce both of these guys. Now, the sodium fluoride here is really just kind of beefing up the fluoride solution in there, adds a little bit more fluoride into that solution. But what we have in this solution is an acid part of the buffer, and we have a base part of the buffer. And that is essential for how a buffer is able to maintain the pH and not get these really big changes. Now, why would a strong acid or strong base not work? Because if you try to make a buffer out of hydrochloric acid and say sodium chloride, and you're like, hey, that's a difference of 1H plus, right? They are related to each other. And that's the same deal we got going on here. That's basically a difference of 1H plus, which is basically what you need for a buffer. The difference, though, is when you dump that HCl into that solution, it is not going to stay together. It's going to completely break apart into H plus and Cl minus. So now when you put the sodium chloride in there, you get some sodium in there and you get some more chloride. So now what you have in that beaker is a mess, but you basically have only the base component, right? You no longer have the acid component because it cannot stay in solution because it's just going to completely break apart. And that's why a buffer cannot be made from a strong acid or a strong base. A strong base would do the same thing. It would just completely break apart. Now, that being said, you could actually produce a buffer from a reaction of a strong acid or a strong base, but the buffer itself is not made up of a strong acid or strong base. So they're completely gone at the end of it. So those two things are really important for how a buffer is able to function, is having those things in the solution at the same time. And again, the difference between the weak acid and the salt of its conjugate base is back to our Bronsted-Lowry definition. Just 1H plus is the difference. And the same thing here with our weak base and the conjugate acids. It is a 1H plus difference. So when you're trying to determine, hey, can I make a buffer out of these two things? These are the two things you should think about. Is anything in that buffer that you want to make a strong acid or strong base? And if the answer is yes, that cannot be a buffer. Second, if it's not a strong acid or a strong base, you need it to be either a weak acid or weak base present. And the other part of the buffer has to be its conjugate partner, which means the only difference between it is 1H plus. So again, that's what you're looking for. So let's actually talk about how a buffer truly functions. Let's start with a non-buffer solution, which is our good friend water. Yeah, water is not a buffer. And if you took some hydrochloric acid and you added it to water, because hydrochloric acid, once again, is a strong acid, it is going to 100% break apart into H plus and Cl minus, 100%. That means if you look at your beaker that you just added the HCl to, the water, you're going to have nothing in there but H pluses, basically, and Cl minuses. And by doing so, this is a little problematic because I am definitely generating a lot of free H pluses really quickly. And that's going to make the H plus concentration in this case go skyrocketing up. And that would also mean that my OH minus concentration is going to go down. And I'm going to see a very big drop in the pH. It's going to become very, very acidic because you increase the amount of H plus, going to drop the pH really far. So if this was, say, a water at a pH of 7, you added some HCl, you maybe find yourself down at a pH of 2 at that point. A really big drop in the pH, a really big change in the pH. Any questions on that there? Now, same thing if you added a strong base to water like sodium hydroxide. If you added sodium hydroxide to water, it also is going to completely break apart into sodium ions and hydroxide ions. And it's basically the same deal. When you pop that into this little guy of water here, it is going to break apart and you're going to produce a bunch of sodiums, which is not too bad. But what is really bad is you're going to produce a lot of hydroxide really quickly. And much like above, you have now produced a lot of hydroxide that's free in that solution. And that means the concentration of hydroxide will increase, the concentration of H plus will go down, and you're going to see that pH start to skyrocket now because you have a lot more free OH minus in the solution. So again, if you start out like a pH of 7, you would see the pH maybe hit 11 or 12 or something like that, a really big jump in the pH. So this is what happens in a non-buffer solution. Basically, you're just producing a lot of H plus really quickly. It's going to have a really big effect on the pH, or a lot of OH minus will have the same sort of effect in the opposite direction on the pH. Now, what will happen if we took this guy, these same guys, and added it to a buffer situation? So I'm going to use the HF and sodium acetate buffer because frankly, I don't want to write acetic acid all these times, like all the books use. So we're going to use HF and sodium fluoride in this case. And by the way, I again do know it is a buffer because again, the difference here is H plus. And by the way, the NaF is actually a salt that's going to break apart to Na plus and F minus. So the real buffering is happening between the F minus and the HF. That is really your buffer part. The sodium here is really just a spectator ion kind of hanging out. And that meets our definition of Bronsted-Lowry, right? The only difference between those two is 1H plus. HF is a weak acid, so that's good. So this is a perfect thing for a buffer. So when I have this buffer solution, because that is a weak acid, it's going to set up, as I mentioned before, that equilibrium in the beaker. So once again, before we even begin in our buffer here, we have both parts that we need, which is we have this guy here, which is our acid part of our buffer, and we have this guy here, which is our base part of the buffer. And you will always have an acid part and a base part to a buffer. As I mentioned before, that's really crucial for how it functions. So now when we take our hydrochloric acid and we add it to this buffer, when I take my hydrochloric acid and I actually add it to this particular buffer, will the hydrochloric acid react with the acid part of the buffer or the base part of the buffer? Which one should it react with? They are called what type of reactions? Acid base reactions is what they're called, right? They're not called acid-acid reactions because that sounds kind of weird, right? So they are called acid-base reactions. So when I add an acid to a buffer, it's going to go and find the base part of the buffer, which is this guy. And we're going to get a reaction between those two, which should be recognizable to you. This is a good old-fashioned double displacement reaction happening here, right? We're going to switch some partners. And we're going to form on the other side some HF and some sodium chloride in this case, right? So again, when we're adding the HCl in this case to our buffer, it's a source of H plus and Cl minus, and it's going to react. Now, when we look at what was actually formed as a result of this reaction, we actually made some HF. And HF was part of our buffer to begin with. And that always happens. You actually use up part of your buffer, but then you actually make the other part of the buffer in these type of reactions. So they're almost kind of self-regenerating part of it. As it uses part of one, makes the other part. So clearly that's not going to screw up the pH because it was kind of there to begin with. And we have this guy here, which is a salt, and we know about this salt, I hope. This salt is what type of salt? Is it acidic, basic, neutral? It is a neutral salt. Sodium from group 1, right? Not going to affect anything. Chloride from HCl, which is a strong acid, will not go through hydrolysis, right? So what we see here, and it's actually what we don't see here, that we did see when we added this acid to water. What do we see when we added the acid to water that we don't see in the other reaction on the product side? We don't see this, right? This is what affects the pH because the pH is equal to minus the log of the H plus concentration, right? So when we added the strong acid to water, we produced a lot of free H plus really quickly. But when we added it to our buffer, we have no free H plus formed, essentially. And what that means is the concentration of H plus stays relatively constant. And if the concentration of H plus stays relatively constant, that should mean my pH should stay relatively constant as well. And I say relatively constant because if you were following it with a pH meter like you'll do next week, you will actually see the pH change. So again, it may go from like a pH of 5 down to like a pH of 4.9, maybe a 4.89 or something like that. But it will not go from like a pH of 5 all the way down to a pH of 1. So you won't see this giant drop in pH. It will move a little bit, and that's good. It should move a little bit in the right direction, but it will not be that giant shift in pH caused by all that H plus that is there. Any questions on that there? Yeah. Say again? You cannot have a buffer that's made up of a strong acid or made up of a strong base. So you cannot say like, hey, this is my buffer. It's made up of like HCl and sodium chloride. It cannot be made up of a strong acid or a strong base. The HCl is not a buffer. This is the buffer right there, the HF and the sodium fluoride. HF is a weak acid and sodium fluoride is its conjugate base. So that's the actual buffer. The HCl in this case is what we're adding to it to see the effect of adding a strong acid to it. And what a buffer should be able to do is resist really big changes in the pH when you add that acid to it. And that's why what we see here is it's able to resist those really big changes in pH because when this H plus comes in, it's going to go find the base part of the buffer, which is in the solution, and it's going to go form this guy. And what that's going to basically prevent is any formation of additional H plus into the solution. So it's going to stop the influx of just free H plus in the solution. Because remember, the pH is really affected by the amount of free H pluses in the solution. So it really gets tied up here with the fluoride and is not freely floating. And that's what keeps the H plus concentration constant in this case. Yeah. Other questions? All right. Then if we were to take the same buffer and we added some sodium hydroxide to it. Now, if I added sodium hydroxide to the same buffer, sodium hydroxide is a strong base. And when we would add it to our buffer, which again, we'll use the same one here, where it's going to set up its equilibrium, where again, we have our base part of the buffer and our acid part of our buffer. When the sodium hydroxide is added, it will go and find the acid part of the buffer to do that acid-base reaction. And what we're going to get in this situation is the sodium hydroxide will add to the acid part of the buffer. We're going to get just a basic, still double displacement acid-base reaction that's going to occur. We're going to form water, and we're going to form a salt like sodium fluoride in this case when we do our double exchange there. So once again here, the sodium hydroxide is really a source of sodium ions going in and hydroxide ions going in, basically in this case. Once again, we see what we saw above, which is we did form more of the other part of the buffer. So again, that always happens. You use up part of the buffer, make the other part of the buffer. That again should not mess up the pH. We see water here, which obviously should not mess up the pH. It is once again what we do not see here that we did see when we added the strong base to water, and that is this guy right here. We saw a lot of free OH minus when we added the strong base to the water, which was not a buffer. And because of that, the OH minus concentration skyrocketed, the H plus concentration went down a lot, and the pH changed a lot. But when we add that same sodium hydroxide to the buffer, we have no free OH minus being formed. And because the concentration of OH minus will stay relatively constant, if you remember, the concentration of OH minus and H plus are tied to each other. As one goes up, the other goes down. So as H plus goes up, the OH minus goes down, and vice versa. That means that our H plus concentration will also be relatively constant. And by default, the pH will remain relatively constant. So the way a buffer is really able to function is it is able to tie up any free H plus from entering the solution when you add an acid. It's able to tie up any free OH minus into that solution when you add a base. Because it has both of those things in the solution to begin with, it's got an acid part to the buffer and a base part to the buffer, so it can handle it when you do that. And because there is no free H plus or OH minus, depending on what you're adding, the pH is able to basically remain relatively constant because of that. Any questions on sort of how that pH buffer works? Now, just to illustrate this one last thing here, maybe. So when we make a buffer, a lot of times we do try to make the buffer with an equal amount of the acid part, HA, we'll call that the acid part, and A minus is the base part of the buffer. So a lot of times we like to start with, an even amount of each of those. So when we add more acid to our buffer, it is going to use up the base part and make some more of the acid part. So dramatically drawn here, not to scale. We will basically make more of the acid part of the buffer, and we will use up some of the base part here of the buffer. And the same thing, if I added more base to the buffer, we will use up some of the acid part of the buffer and make more of the base part. So we'll make more of the base part of the buffer, and we'll use up some of that acid part of the buffer. Now, there is a thing known as buffer capacity. You can blow through your buffer. Let's just say you were not paying attention while you're doing lab, which would never happen. And let's say you had a choice of 3 or 4 different HCl's, one of them being 0.1 molar and one of them being 18, and you decided probably not a big difference there, right? I'm just going to grab the 18 molar HCl and pop it into the beaker. Nothing bad should happen, hopefully. You will probably add so much H plus that you'll blow right through the base part of your buffer if it is not the right concentration to handle that. And you will, at some point, once you blow through your buffer, start to see a pretty big jump or drop in the pH at that point. It is possible. Also, as you can imagine here, if I just kept adding acid, right, every time I add acid, I'm using up the base, right? So if I just keep adding acid, at some point I could blow right through that buffer. Or if I just kept adding base, I could blow right through that buffer. By the way, that is what happens when you do a titration. And we'll talk about that when we talk about titrations. But if you ever wondered why you add one drop and all of a sudden your indicator went super dark pink, and I just added one drop, it's because you just blew through your buffer and it just had a big jump in the pH. And as we saw with the acid-base indicators, they work on a pH range, and your little colorless solution just went super dark fuchsia pink, right? With one little drop. And so a titration is just that. Actually, we'll talk about you make a buffer and then you blow right through it as you continue on with your titration. And that's why you can see a pretty big jump in your pH indicator when you do that. So there is a buffer capacity. It's really important when you make a buffer that you make it with the right molarity to handle whatever acid and base that you're adding into it. How do you know how to make a buffer? What should you choose to make a buffer? You could use your friendly neighborhood Henderson Hasselbalch equation, which is really the equation that you should use for buffers, and only buffers is where you should use this equation. Now, if I were to make the base part of my buffer and the acid part of my buffer equal to each other, and I put that into my Henderson Hasselbalch equation, I would get the pH is equal to the pKa plus the log of 1, right? Since the base and the acid equal each other, right? It's the same number, equals 1. Log of 1 equals 0. That means this is the relationship that if you were looking to choose what you should make for a buffer at a specific pH, you would want to choose a weak acid or weak base with a pKa value of plus or minus 1 of your pH value. So if you wanted to make a buffer with a pH of 4.5, acetic acid is your choice. It has a pKa value of 4.74. That's a really good choice. If you wanted to make a buffer with a pH of 9.1, acetic acid is a crappy choice because that's very far away from 9 to 4.74. You're going to be there all day, and it's not going to work so well for you to try to make that buffer, and they're going to yell at you while you're using up a lot of supplies to try to make that buffer work. A much better choice would be something like ammonia, which is a weak base with a pKa value of 9.25. That would be a much better choice, ammonia and ammonium chloride, and you can make your buffer much nicer in that situation. So if you have to make a buffer at a specific pH, you want to choose either a weak acid or weak base, again, that has a pKa value as close as you could get it to your desired pH, and that's going to make it much better. When you actually go and make this buffer, when you decide to make it, it will most likely not turn out with the exact pH that you need. And that's okay too, because buffers resist really big changes with acids and bases when they're added. Most of the way that you make a buffer is, oh, I didn't really get the pH I need. You could actually dial in your pH you need by adding either acid or base, depending on which way you need to go, up or down. And you could literally drop by drop dial in your pH to exactly what you need by adding some acid or base to your buffer, because when you add those drops, it's not going to have big changes in pH. It's going to have very, very small changes in pH. And you can actually dial in your buffer to the correct pH it should be before you maybe use it in